A rocket has to fly slow and fast in the same flight, subsonic on the way up, and supersonic later. And optimizing your design for one of those speeds can actually break how it performs at the other. Here's how I ran into that problem and how I fixed it. This summer at Northwestern, I designed a rocket body and a nozzle in SolidWorks, then ran both through flow simulation at subsonic and supersonic speeds to see how they'd actually perform, not just what they'd look like on paper. But before I get into the video, let's answer a common question, being, why does a rocket's nose tip look different depending on how fast it's flying? For me, I designed mine for subsonic speed, but understanding why supersonic tips look completely different taught me a lot about how my own design worked and how it didn't. At subsonic speed, air has time to move out of the way before the object gets there, or in our case, our rocket. Air flows smoothly around a rounder nose without a problem. At supersonic speed, the object is moving faster than the air can get out of its way, and that creates a shockwave, a sudden jump in pressure right at the nose, because the air in front of the tip literally can't move aside in time before more air is jammed right at it, and this also creates the well-known sound and term called the sonic boom. A blunt or rounded nose makes that shockwave sit further out from the surface, which spikes drag extremely hard, and also at the same time provides a lot of stress. A sharper, more pointed tip lets the shockwave sit closer against the surface, cutting that drag. That's why supersonic aircraft and rockets have those needle-like noses, and subsonic ones don't need them. Additionally, that's why when we want high speed, surface area becomes our biggest enemy. This is why javelins and arrows are designed to be so thin and narrow. Their minimal surface area allows them to effortlessly slice through the atmosphere with very little air resistance. On the other hand, a blunt object like a beach ball has a massive surface area that smashes into air molecules all at once, creating a wall of drag that immediately acts like a parachute and forces it to move slowly. But surface area isn't the only thing creating drag. Every time, let's say, a wing generates lift, it also creates vortices at the tips, and those vortices create their own type of drag, called induced drag. It doesn't come from friction against the surface, it comes from energy getting spent spinning up a spiral of air instead of pushing the wing forward. But why does this happen? A wing makes lift by keeping the air below it at a higher pressure than the air above it. So at the tip of the wing, that separation runs out, so the high pressure air underneath curls around the edge to reach low pressure at the top. The wing is also moving forward the whole time, so that curling motion gets dragged backward with it. And curling plus getting dragged backward is what makes a spiral. That spiral is the vortex. And this is a real phenomenon as well. There's actual footage of an owl flying through a wall of soap bubbles. Watch the wingtips. That spiral pulling through the bubbles, that's the vortex made visible for us to see. But this isn't strictly tied to only wingtips. This is the exact same thing on my own rocket. When I ran the sim, you can see that the streamlines curling into that spiral right off the edge of the fin. Same mechanism as the owl, same mechanism as any wingtip, just showing up here because there's a pressure difference and an edge for the air to curl around it. So then, how do we fix this? Well, you see, the vortex only forms because there's a hard edge for the high pressure to curl around. So the fix is simple, change the shape of the edge so it's harder to curl around. And that's what a modern winglet does. Here we have a normal airfoil, we can see how and where the vortices are formed, whereas the wing on the right has winglets, which is the upward bend you see a lot of modern plane wings have. So instead of the wingtip just stopping flat, it curves, which breaks up that clean curling path the air wants to take. The vortex still tries to form, but it's smaller, weaker, instead of one big clean spiral. Smaller vortex means less energy stolen to spin it, which means less induced drag, which means the engine's thrust goes further. And that's how our rockets are able to achieve faster speeds. Okay, now we've solved the issues on Earth, but how do we escape Earth and go to space? First of all, there's two major forces acting on my rocket: compression and tension. Compression is when something gets pushed together, like squeezing this pencil from both ends. Tension is the opposite, pulling apart, stretching it. So what does that actually look like on a rocket? This is my rocket model, and the sim is showing exactly that. compression and tension acting on the structure. However, I've exaggerated the deformation by 1,000 times here so you can actually see it happen. In real life, this movement is way too small to see with your eyes. Picture this water bottle, but made out of pure titanium and aluminum alloy that is used on rockets. When I compress it or I stretch it, it still moves, just barely and way less than the steel that my water bottle is made out of wood. Even the strongest materials flex a little under load. Nothing is perfectly rigid. And that's actually critical for an aerospace engineer to account for. If a structure can't handle repeated compression and tension without failing, especially on something millions of tons, it's a real problem. And it gets worse leaving the atmosphere since you're dealing with extreme heat on top of the mechanical stress. That's why only a small handful of materials can actually survive both at once. So that's the rocket. We covered why nose tips need to be sharp at supersonic speeds and rounder at subsonic, and how that comes down to shockwaves, otherwise known as sonic booms. We compared a beach ball and a javelin to show why surface area alone creates drag. We talked about vortices, why they form, what they actually look like on my own rocket, and how winglets cut down the induced drag they cause. And we looked at compression and tension, the two forces every part of this rocket actually has to survive. Next time, I'm getting into the nozzle, thrust, fuel efficiency, and why a rocket needs more fuel than you'd think just to get itself off the ground. But that's for part 3. If any of this made sense, or if it didn't, let me know in the comments. See you in the next one. All the CAD files, the write-ups, everything is linked in the comments, so if you want to actually dig into it, please do.